Hi, today we're going to be looking at a topic which is actually a continuation of the previous topic that we learned on thermal expansion and linear expansivity. Today we're going to be looking at area expansivity, and from what we have on the board, thermal expansion is not only restricted to the length alone. That is, maybe a solid does not only increase in its length due to a temperature difference alone, but it also involves the increase in all dimensions of the solid. That is also in the area of the solid as well as the volume of the solid. Expansion can also occur there. Now, area expansivity in brackets beta is defined as the increase in area per unit area per degree rise in temperature. Mathematically, we can write this definition as area expansivity, which is given as beta. This is a Greek symbol. Um, is the change in area or the increase in area per unit area. That's the original area, and then per degree rise in temperature. In the former one, I used T, and then I told you that temperature can still be used as theta. Let me just maintain it as T to avoid any confusion. Per degree rise in temperature, where my change in A is given as the change in area or increase in area, which is also the something as the new area, that's A1 minus the original area A0. My A0 is the original area of the solid. My change in T is increase in temperature, which is something as the new temperature minus the original temperature. That's my change in T. And then finally my beta, which is the area expansivity. And the beta also is equals to 2 times of the linear expansivity. Have this in mind. We can be given a question to solve, and then parameters will be given, and the linear expansivity might also be given, and then we are asked to find the area expansivity. Just multiply it by 2, and then you get your value for that. All right, here we have a question. A brass disc has a hole of 10 cm in diameter punched in its center at 10 degrees Celsius. If the disc is placed in a boiling water, what will the new area of the hole be? Okay, now let's write out the parameters we have. Let me divide this board into two. We are given what the solution. We are given the diameter to be what? 10 cm. Okay. Now this is a circular disc. A brass disc has a hole of 10 cm in diameter. So we know that this is a circular disc, and the area, which is the original area of the circular disk is what? Pi d square over 4. That's from the area of a circle. And that will give us what? 22 over 7. That's for pi times d square over 4, which is the d is 10 square all over 4. And that will give us what? 22 over 7 times 100 over 4. Now when you multiply this, you'll be getting 78.54 cm square. 78.54 cm square. That's for our original area A0. Now we've gotten our A0. What is the original temperature? That's at T0 is for 10 degrees Celsius. And what do you think our new temperature will be? If this is placed in the boiling water, what's the temperature of a boiling water? 100 degrees. Now from here we can get a change in T, which is what? T1 minus T0. And that will give us 100 minus 10, which will give us 90 degrees Celsius. That's a change in temperature. Okay, what else can we get from here? They gave us our linear expansivity alpha to be what? 1.0 times 10 to the power of negative 5. Now we're not dealing with linear expansion, we're dealing with area. So our beta from the formula I gave to you is always 2 times of the linear expansivity. And that will give us that our beta is equals to 2 times 1. That will give us 2.0 times 10 to the power of negative 5. Okay, now what is our formula? And we are asked to find what would the new area of the hole be? That's our A1. What will A1 be? We don't know it. But if I can get the change in area, which I know is what? A1 minus A0, I can then get the value of the A1 from here. So let me first of all solve for the change in area, and then I can then transpose the original area over here and then get the new area of the disk. Now the formula is beta is given by the change in area all over the original area times change in temperature. All right, let me clean off this side and solve. We have it that what's the value of beta 2.0 times 10 to the power of negative 5 equals to what's a change in area? We don't know for now. All of what's the original area? That's 78.54. Now times what's a change in temperature? 90. I can call this one all over 1. Now cross multiply change in area will give us that I have 78.54 times 90 times 2.0 times 10 to the power of negative 5. Now multiplying these two things out, let me use my calculator. I will have the 78.54 multiplied by 90 multiplied by 2, and that will give us that my change in area is equals to 14137.2 times 10 to the power of negative 5. I can change this into standard form. I'll move to the left 5 times. 1, 2, 3, 4, 5. That will give me that change in area. It will be 0. Let me approximate to 2 decimal places. 0.14 times 10 to the power of 5 times 10 to the power of negative 5. These two we cancel out from the law of indices. So my change in area, sorry, will be 0.14, 0.14 cm square. And that's not what we are after. We are after the new length, that's our A1. And from the formula here, change in area is equals to A1 minus A0. Let me just transpose this over here. A1 will then be equals to change in area plus A0. Let me clean up this side a bit. And that will give me what was a change in area 0.14, that's my A1, equals to 0.14 plus what was my A0, 78.54 plus 78.54, and that will give me that my new area is equals to 78.68 cm square. Yeah, that's the new area of the disk. Okay, yeah, we have another question. A fridge made of steel is 600 meters long. What is the daily variation in its length if the nighttime and daytime temperatures are 10 degrees Celsius and 30 degrees Celsius, respectively? And then linear expansivity of steel is 0.000012 per degree Celsius. Okay, now let's write out parameters first of all. We have our original length as a L0 to be equals to what 600 meters. This is a question involving linear expansivity now, not area. And then what else was given to us? Change. I mean the temperature differences. We have that our T1 here is equals to what 10 degrees Celsius. T, I mean our T0, sorry, and then our T1 is equals to 35 degrees Celsius, and our alpha. Now let's change this alpha to standard form. As moving to the right, one, two, three, four, five. That will give us a 1.2. Since we move to the right, it now become a negative 5 per degree Celsius. Okay, now what will be asked to find? The what is the daily variation in its length, and it means the change in length. That's by how much does the length of the fridge change on a daily basis. That's a change in length is what we are asked to find. Now from the formula I gave to you that alpha, which is the linear expansivity, is equal to the change in length all over the original length times change in temperature. Was my alpha, that was a 1.2 times 10 to the power of negative 5, because what's my change in length, which is unknown. Original length is what 600. Change in temperature, did I solve for it? No. And that will be change in temperature is equals to T1 minus T0, and that will be 35 minus 10, which will give me what 25 degrees Celsius. So here will give us 25 degrees Celsius. And call this one all over 1. Now cross multiply, I will have that my change in length is equals to 600 times 25 times 1.2, now times 10 to the power of negative 5. Um, Let me press my calculator to get the answer for that multiplication. I have that 600 times 25 times 1.2, giving us 18,000. It will be 18,000 times 10 to the power of negative 5. Changing the 18,000 to standard form, let's move 1, 2, 3, 4, 5. That'll give us a change in L is equals to 0.18 times 10 to the power of 5, because I moved to my left, times 10 to the power of negative 5, which was here initially. Now these two will cancel out from the law of indices. Now change in length will give me what? 0.18. Um, what unit are we using? Meters. So this is the daily variation in the length of the fridge. Here is another question. Very interesting, I must say. The linear expansivity of a metal P is twice that of another metal Q. When these metals are heated through the same temperature change, their increase in length is the same. Okay? Calculate the ratio of the original length of P, that's of metal P, to that of metal Q. Okay, let's solve this. Now from the question, they said that the linear expansivity of a metal P, you can say that let the linear expansivity of the metal P be given by alpha P of a metal P. Let the linear expansivity be alpha subscript P. I said is twice that of another metal Q. That is, it is 2 times um, the linear expansivity of another metal. Let me call it metal Q. Metal Q. That's alpha P is equals to 2 alpha Q. Okay. Now, when these metals are heated through the same temperature change, that means they have the same change in temperature. The change in temperature of metal P is the same thing as the change in temperature of metal Q. Okay, their increase in length is the same. That means the increase also in length of metal P is the same as the increase in length of this metal Q. We are asked to calculate the ratio of the original length of P to that of Q. Okay, let's say, let me denote the original length of meta P as LP, and then let it stand for original length of P of meta P, while LQ, let's stand for the original length of meta Q. Now, what's the formula for linear expansivity now? It's given by alpha is equals to change in length all over original length and then times change in temperature. Now let's try and make this change, this original length, the subject of formula. I can call this one all over 1, cross multiply. I'll have that this will multiply this, while this multiplies this. That's alpha times L0 times change in T is equals to change in L times 1, which is the same as change in L. Now I can divide both sides by what? Alpha change in T to cancel this out. That will give me that alpha L0 change in T all over alpha change in T is equals to change in L all over alpha change in T. This will cancel this. So my L0 is what? Change in T all over not change in L, sorry. Change in L all over alpha change in T. I think so. Yeah. Okay. Now let's lock in this. The LP is something as calling it as change in P all over the alpha of P and then change in T. Let me maintain it as changing since they are changing length and changing temperature are the same, right? L of Q is equals to still change in L since both of them are the same all over the alpha of Q times change in T. Remember that the change in length and the change in temperature are the same. Now we're asked to find the ratio of the original length of P. That's the ratio of this to this. Okay, let me clean up this side and solve it here. The ratio of LP to LQ as LP ratio LQ. That will give me change in L over, what was my alpha P? We said that it is equals to 2 times of alpha Q. That's 2 alpha Q. Remember from here, they said that the linear expansivity of meta P is twice that of the linear expansivity of meta Q. So let me slot in place of alpha P, let me put it as 2 times alpha Q. Then change in T ratio. What was my LQ? That's change in L all over alpha Q change in T. Remember that ratio also means division. I can write it as change in L all over 2 alpha Q change in T divided by change in L all over alpha Q change in T. Change the division to multiplication. I have that change in L all over 2 alpha Q change in T times alpha Q change in T all over what? Change in length. Change in length, yeah. Now something can cancel out. This can cancel out this. Change in T can cancel out change in T. Uh, Alpha Q can cancel out alpha Q. So I'm left with here will give me 1 all over what is here 2. So the ratio of as the ratio of LP over LQ, that's LP ratio LQ, is giving me something as 1 over 2. So the ratio of LP to LQ is equals to 1 is to 2.